Can you please mute yourself? Good morning. I request the participants to kindly mute themselves.
This principle. Welcome to Murray Lakshman Reddy Group of Institutions, providing world-class education and research facilities to help transform people's lives for the better. It is the brainchild of a visionary who conceived and promoted it in 2005, providing world-class education and research facilities. Meet the man, Sri Murray Lakshman Reddy, who ushered in the silent mission. A mission to provide technological advancement from time to time, promoted it in 2005. With the aim of imparting education with global standards to enrich values with knowledge in the silent mission. Succeeding the mission to provide Sri Murray Lakshman Reddy, making education a positive experience. Sri Murray Rajashekhara Reddy, founder secretary, nurtured MLR Group of Institutions to win the pride of being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. Sri Murray Rajashekhara created in vast and peaceful area of 35 acres. Students here tend to learn, experimenting their life projects through centers of excellence, which is tied up with various industries. Spacious and comfortable classrooms, created corridors and advanced laboratories with equipped ultra-modern audio-visual technology auditorium accommodating 1,000 plus audience, separate hostels for boys and girls, each student especially taken care for the provision of facilities and hygienic food in spacious and eco-friendly canteen, etc. Our salient features similar group of institutions AICTE recognized MLR group of institutions accredited by NAC with A grade and has MBA accreditation for all programs. MLR Sports Complex and inaugurated institutions with most advanced sports facilities like cricket stadium, badminton court, table tennis, billiards, and basketball. MLR Sports Complex organizes many national and international university-level sports fests by grooming every aspirant in competing national and international sports forums and successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at various national and international sports events. MLR Group providing free admissions every year by supporting aspirant under sports quota with scholarships for the meritorious sport persons to pursue their career in sports and opportunities in government sector. To sharpen and educate students' creativity and entrepreneurial skills, MLR Group has established Center for Innovation and Entrepreneurship. Facilities like Social Square, Innovation Hub and Makerspace. The Makerspace is a technical prototyping platform for students' innovation and invention, which is loaded with ultra-modern equipment such as multimedia workspaces, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8 plus market-ready products and supported 11 plus student startups. MLR Group has set up livelihood business incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology for livelihood-based enterprises. Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25 plus funded projects, 700 plus SCI or Scopus journal articles, and 35 plus intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced Indo-Universe Collaboration for Engineering Education IUCEE to introduce outcome-based student-centric education and Bloom's taxonomy-based teaching, learning and evaluation process projects in community services, EPICS, in association with Purdue University, USA. Scope, School of Programming Practices to hone the coding and programming skills. Students Platform for Engineering Education Development. STEAM empowers the students to become a factor of change in engineering education and its effect on society and environment. Referee to organize NUN, TEDx Talks and Techno Cultural Fest to uplift student communication and English skills to the global forum. MLR Library is fully loaded with diversified study materials, books, national and international journals with dedicated digital library, along online subscription to massive open online courses, IEEE, Elsevier, Springer, ACM journals, etc. MLR assures the safety and security of the students. Its transport infrastructure includes modern and secure vehicles and strictly complied with RTA regulations with well-maintained safety standards. MLR Group of Institutions having faculty of nationwide experienced and renowned adjunct professors include the expert scientists of DRDO, DRDL, HAL, BHEL, SAE India, ECIL and JNTU imparts education with pure practical inputs. Offers courses in BTech, Aeronautical Engineering, Computer Science Engineering, Civil Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Information Technology, Mechanical Engineering, MTech with Aerospace Engineering, Computer Science Engineering, Embedded Systems, Digital Systems and Computer Electronics, CAD or CAM Engineering, Thermal Engineering, MBA courses. MLR proudly announces that till now 75% of their students have grabbed the opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education. The opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education. The opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education. The opportunities with average salary package of 6 lakh by holding premier
Growing businesses need a hosting solution that is powerful yet easy to manage. Let's look at how business
Yeah. Good morning, everyone.
Good morning.
Uh, so, just a minute. Actually, there was a technical problem here. So, good morning. Welcome to the participants for the third FDP on recent developments in the nano composites and smart materials in the aerospace industry. So, this is a third of the kind in AICTE STTP workshop, and we have here the chief guest for today's function, Dr. N. Kishore Nath, sir, and our beloved principal, sir, who has been propelling us throughout for conducting such workshops. So, welcome to the session, sir. Welcome, Principal Dr. K. Srinivas Rao, sir, and Dr. Kishore Nath Naini, sir, Scientist G for the session. So, Principal, sir, please address the gathering.
Yeah, good morning, Sweta and Dr. Kishore Nath, sir. Good morning, sir. Uh, so, Dr. Kishore Nath, sir, is our well-wisher of the institute. And once again, I welcome to this AICT-sponsored workshop on recent developments of nano composites and smart materials in the aerospace industry. So, at the outset, I congratulate the Department of Aeronautical Engineering for organizing this prestigious AICT sponsored workshop. And I welcome Dr. N. Kishore Nath, sir, Scientist G, Project Director, Veda Advanced Systems also. And the speakers of these sessions, so Dr. V.L. Satish, scientist, and I. Srikanth, scientist, G. ASL DRDO, Dr. Sudhir Kamble, Dr. Muhammad Talla, Dr. Manas Das, Department of Mechanical Engineering, IIT Guwahati. So Dr. S. Sharma, Department of Mechanical Engineering, IIT Jodhpur. And Dr. Vel Murugan, Professor, Department of Aerospace Engineering, IIT Madras. So Dr. Ramesh Babu Vemuluri, Mechanical Engineering, VIT. So Dr. Lokasani Ban Prakash from our institute. Finally, Dhananjay Das, Sir, Data Scientist, Entity Data, Chennai. So I'll welcome all the participants and all these resource persons to the brief about MLR Institute of Technology. So let me brief about the situation now. It's been some tough time since the last 7 to 8 months. All of us have gone through quite a bit. And we understand that this is a challenging and unexpected time, but things like this should not stop us from moving forward. And this is another opportunity for us. We'll be connecting with all of you virtually. And we have conducted two workshops like this, and there is a very good response. And the participants are also empowered in the technologies. And just 2 minutes about MLR Institute of Technology. In the 16 years of existence, MLR Institute of Technology has established itself as a premier institution. And I also consider it's my privilege to be associated with such a prestigious institution. So I am proud to say that MLR Institute of Technology is escalated to great horizons of success. It has become synonymous with academic excellence and a benchmark to measure co-curricular excellence, and also a center which creates responsible citizens. In addition to empowering the students, and we are also keen on empowering the faculty. And we are very grateful to our Honorable Secretary because of his valuable guidance, encouragement, and support that this all has been possible. And MLR Institute of Technology is the youngest institute of Tier 1 accredited institute across Telangana, and is conferred autonomous status by UGC in the year of 2015. So MLR Institute of Technology offering 7 UG programs, which includes emerging areas like artificial intelligence and machine learning, data science, cyber security, in addition to the traditional engineering programs. And for PG programs, we are offering in engineering in addition to MBA. So with this, this has been great. And once again, I'll welcome Dr. Kishore Nath sir for his valuable guidance and support and mentoring of this institute. So I must thank for giving the opportunity to speak in front of you regarding this development program. Go ahead, Shweta.
ఒకటే స్లో చేయండి మరి వేరేది
request the
వచ్చినప్పుడు నేను
participants.
నేను కాదండి సార్ ఎలా ఉన్నాయో డబుల్
I
స్టాండ్
request the participants to kindly mute themselves. Thank you very much. So thank you very much, sir. It is a pleasure to host this program for all the things, for all the participants who are from Jammu and Kashmir to Kanyakumari and Punjab to Sikkim. We have the participants, and only COVID and online had made this possible for us meeting. And we have the professors from IITs, from DRDO, from NAL, and their appointment had been a little easy when compared to an offline program. So we have for today's session, the first session, we have Dr. N. Kishore Nath with us, who has been always mentoring us throughout and also in preparation of syllabus and all. So Dr. Kishore Nath, he is presently working as Scientist G and the Project Director for Veda Satellite Launching Vehicle in Advanced Systems Laboratory, DRDO. He is having 24 years in the design and development of advanced composites and aircrafts, materials used for aircrafts. He designed and developed composite flame detection, deflector, radome warhead for Prithvi. He has been a part of Tejas, Agni 4, Agni, where he developed composite grid stiffened plates, composite rocket motors, and has given his expertise. Publication. He's having 13 papers in national and international journals, 25 papers in the conferences, delivered over 40 plus invited talks in various workshops and symposiums at various universities. He's been awarded DRDO Laboratory Scientist of the Year, Outstanding ISAMPE Outstanding Design and Process Development Award for the development of externally mounted jettisonable composite fuel drop tank for Tejas, our indigenous aircraft, by the President ISAMPE. The Best Technology Researcher Award for the development of flex nozzle systems for Agni 4 at Third Technology Achievement 2015 New Delhi. Agni Award for Excellence in Self-Reliance. Best Scientist Award for development of titanium components for composite rocket motor casing at 7th Science and Technology Awards 2018 at Bangalore. National Design Award in Mechanical Engineering 2019, awarded by National Design and Research Forum. He is a member of many professional societies like IEI, SME, ISME, SRSI, HMA, SFA, ISAMPE, SSI, ISTE, ISSSE, and Indian Science Congress Association and Society for Aerospace Quality and Reliability. So, sir, it is a pleasure to host you, and I hand over the mic to you.
Madam, shall I share the screen?
Yes, sir, you can share the screen.
Thank you.
So your screen, hello. So your screen is not visible properly. Kishore Nath, sir.
1 minute, madam. I'm opening.
Yes, sir.
Madam, are you able to see my screen?
Sir, I can see only your desktop, sir, not your PowerPoint.
1 minute, 1 minute. Something. రెండు సార్లు ఓపెన్ అయింది ఒకసారి.
Sir, it is visible, sir.
Now it is visible. Okay, madam.
Yes, sir. Thank you.
Good morning, all. I thank MLRIT management and Principal Dr. K. Srinivasa Rao, Dr. Gupta. I am head of the Department Aeronautical Engineering for inviting me to this FDP program on smart materials and nano composites. I am seeing in the lockdown period, MLRIT is organizing number of programs to keep the faculty and students engaged in the academic research work. I congratulate MLRIT in taking this initiative and continuously conducting one or the other programs. So I am happy to be part of this FDP program and delivering a lecture on smart materials and composites, which I have been involved in developing for aerospace and missile applications. Smart materials are the today's materials where it is engaged in involving the materials with sensors and other applications. 1 minute, madam, I am unable to progress. Okay. Smart materials involves basically sensors, actuators, controllers, and structures. As you see in this diagram, actuators will be involving to give the force to the required material, and the controller which controls the how much force we have to give, and sensors will sense how much force we are giving, and the feedback mechanism will be there, and the structures will respond depending upon the requirement. So smart materials are the new generation materials surpassing conventional structural and functional materials. These materials possesses adaptive capabilities to external stimuli such as loads or environment with inherent intelligence, mutation of different characterization. So smart materials will have the sensing capability and the actuation capability. In real-time scenario, it will sense how much force is required, and it will give the required force to the structure in order to protect from the environment or from the external forces which is coming. Smart materials are basically classified into two categories: active and passive. So active passive smart materials are materials possesses the capacity to modify their geometric or material properties under the application of electrical, thermal, or magnetic fields, thereby acquiring an inherent capacity to transduce energy. Examples of active smart materials are, as you know, piezoelectric materials, which is used in various structures in order to give the different loads. Then shape memory alloys, which gives different shapes depending upon the environment. If you heat, it will regain its original shape, and if you cool, again it will give some actuation force. So electrorheological fluids and magnetostrictive materials, these can be used as a force transducers and actuators. This already we are using in many of our missile applications and aircraft applications, this shape memory alloys for the different applications, which I will be explaining in my due course of presentation. So sharp memory alloys has a large recovery force of the order of 700 MPa, which can be utilized for actuation. Similarly, piezoelectric materials which convert electrical energy into mechanical force are also used for different applications. So passive smart materials, although smart, they lack inherent capability to transduce energy. For example, fiber optic materials is a good example of passive smart materials. Such materials act as only sensors, but not as actuators or transducers. So different types of smart materials. Piezoelectric materials are the very common examples of such materials where they produce voltage when stress is applied. Since this effect also applies in the reverse manner, the voltage across the sample will produce the stress within the sample. Suitably designed structures made from these materials can therefore be made that bend, expand, or contract when voltage is applied. So piezoelectric materials are very commonly known materials which we are already experiencing in various structures and environments which can relate to our day-to-day life. Thermoresponsive materials, either shape memory alloys or shape memory polymers, are materials that can hold different shapes at different temperatures. So shape memory alloys basically, depending upon the temperature, it will vary the shape, and if you change the temperature, it will go back to its original shape, or if you heat the material, it will take the new shape which you want. So with this, we can alter the shapes and also experience the forces or stresses which are required for our day-to-day monitoring. Magnetostrictive materials similar to piezoelectrics respond to only magnetic fields rather than electric fields. They are typically used in low frequency, high power sonar transducers, motors, and hydraulic actuators. Along with the shape memory alloys, nitinol magnetorestrictive materials are considered promising candidates for achieving active damping vibrations. So pH sensitive materials change their color as a result of changing acidity. This can be applicable for paints that can change color to indicate corrosion in the metal underneath them. So chromogenic systems change color in response to electrical or optical or thermal changes. Electrochromic materials which change their color or opacity on the application of voltage. Very common examples of such types is liquid crystal display materials. Polymer gels such as hydrogels have a cross-linked polymer structure inflated with a solvent such as water. The gel has the ability to swell or shrink up to 1,000 times. Changes in example of temperature or pH of the material. So what are the various types of applications of the smart materials? It can be used for self-repair, like embedding thin tubes containing uncured resin into the materials. When damage occurs, these tubes break and exposing the resin which fills or damage and sets. Self-repair could be important in inaccessible environments such as underwater pipe or in space. Suppose in space, if any satellite structure gets damaged because of the environment, so we cannot go and repair. It will be very costly. So if you embed the smart materials, when the structure breaks, it will embedded tube will break, and it will fills the gap with the resin placed over there, and the structure will become again functional. So this type of smart self-repair kits are available, and in various aircrafts also this is in practice. In the field of defense and space, to suppress the vibrations and shape change in helicopter rotor plates, shape memory alloy devices are also being developed that are capable of achieving accelerated breakup of vortex waves of submarines, and similarly different adaptive control surfaces developed in airplane wings. So in nuclear industries safety of the for enhancement of safety, personal exposure reduction, life cycle cost reduction, and performance improvement, the smart materials are extensively used. In structural engineering, they are used to monitor civil engineering structures to evaluate their durability. So smart structure, what is meant by smart structure? Smart structure will have 4 components like actuators, sensors, electronics, and control systems. So if you see the actuators, adaptive response to shape memory alloys, piezoelectric devices, MR fluids, the environment, adaptive response to the environment, then sensors gather the information, optical fibers like piezoelectric materials, and it gives to the controller, electronics, transfer of information, signal detection and control. So the smart system will consist of a smart structure with sensors, actuators, and control system. What are the smart structures? The current composite materials will capitalize on novel material characteristics to exploit the emerging technologies for the synthesis of smart structures, systems, and related technologies. These innovative materials and related technologies will be utilized in nanotechnology, biomimetics, microelectromechanical systems, MEMS. Self-repair, self-diagnostics, self-multiplication, and self-degradation are some of the characteristics of these smart structures. So multifunctional materials and adaptive structures. It have intrinsic or extrinsic capabilities to respond to an external stimulus in a useful manner. The external stimulus being sensed could involve a change in material's environmental conditions, such as light, temperature, pressure, humidity, electric field, and magnetic field, etc. The response to an environmental change would involve a change in one or more of the material's physical properties, such as size, shape, color, structure, conductivity, magnetization, or polarization. So enabling technologies for adaptive structures. An adaptive structure has three basic components like sensors, actuators, and control systems. The performance of these components dictates the overall performance of the adaptive structure. Considerable research and development activities have been directed towards realization of appropriate sensors, actuators, and control systems for the customized adaptive structural applications. The technologies related to sensors and actuators are primarily based on physical phenomena, device concepts, designs, material properties, and material processing technologies. Sensors. So the application of energy field on a material generates a change in its characteristics. In sensor materials, a slight change in energy field can produce a significant change in one or more characteristics, and this change can be detected. So in order to get the sensor feedback is a must in a sensor. So sensors and feedbacks are in a closed loop. So the response of sensor material can be either mechanical, electrical, optical, magnetic, thermal, or chemical. For adaptive structural applications, the most useful response is electrical, which can be monitored and analyzed by control systems. Now, because of the digital systems, wherever we want any feedback to be happened, digital signals will be very useful, unlike analog signals. So optical strain sensors have been developed within the past few years for aerospace and space applications. So the types of smartness in structures, as explained earlier, closed loop and open loop. Closed loop smart structure senses the changes to diagnose the nature of the problem, takes action to mitigate the problem, and also stores the data of the episode for future references. Open loop SmartNet design is such that structural integrity is enhanced only when needed, and the structure relapses to its normal state when there is no need for enhancement. So biomimetics. Biological structures are all smart structures. So if you mimic biological structures, the smart structures, we can implement it mechanical or electrical systems. Biological structures or systems are the smartest, and in terms of energy consumption, the most economical. These are sensors, nerve cell acts as sensors, actuators acts as muscles, control center acts as a brain, and the host structure, the body with or without both. A source of energy is also needed. So as you see in the diagram, distributed control center, the brain will control, it is like a control center, and the sensors and the body, the power, and the sensors will act as actuators will act as a closed loop system, so that we can mimic the biomimetics. So man-made smart structures are on an evolutionary path in the following sequence. You can see the various smart structures as explained here. Actively smart structures will have sensor, feedback, and enhanced actuation system. Very smart structures will have sensors, feedback, enhanced actuator action, plus one or more other biomimetic features. So intelligent structures actively smart structure endowed with a learning feature so that the degree of smartness is increased with experience. So there are wise structures. They are called wise structures because moral and ethical decisions also they can take. Consciousness in smart structures, collective consciousness. The internet is adaptively already playing a role in some kind of collective consciousness of the for the planet Earth, and is much more is still yet to come. So the man-made integration, the man-machine integration with intelligent structures is the order of the day. So the both wiseness and intelligence is built into these features. Shape memory alloys. It has the ability to return to its predetermined shape when heated. So shape memory alloys are basically used wherever there is a force required. If you change the temperature, the force can be obtained by change in the shape of the materials. So we are using a lot of shape memory alloys in our aircraft and missile applications. So when this alloy is in below transformation temperature, it undergoes low yield strength and will deform easily into any new shape, which will be retained. If this alloy is heated above its transformation temperature, it changes its crystal lattice structure, which returns to its original shape. Shape memory alloys are remarkably different from other materials, are primarily due to shape memory effect and pseudo-elasticity, which are related with the specific way the phase transformation occurs, biocompatibility, high specific strength, high corrosion resistant, high wear resistant, and high anti-fatigue property. Shape memory alloys are taking active shape in all the new generation aircrafts and missile systems, which is extensively used for complete remote applications. Shape memory alloys are used in many applications such as aerospace, medical, automobile, tubes, controllers for hot water valves. The phase transformation process for shape memory alloys. So you can see pictorially it is represented when the material is in circular shape. When its temperature is changed, it takes a new shape, deformed temperature. Again, when it is heated, and again it comes back to the original shape. The deformed shape can be used to have an intelligent operation, whichever required for us, either force or stress. Phase transformation process for shape memory alloys. You can see this is basically a metallurgical marvel. So if it is cooled, the austenitic behavior will change into martensite behavior. And again, when it's heated, it comes back to austenite. So for this property, we are using for different applications. So the change in material shape, which is acting as a force, is converted into actuation force. So smart actuators, which gives force whenever required as per the structural applications. So what are the smart actuators? Recent developments of microelectronics and communications have widely contributed to the evaluation of sensors and actuators and have given rise to an increasing interest in distributed intelligent systems. The local data processing capabilities associated with the sensors and actuators give them new functionalities, promoting them to the status of smart sensors. So we are using number of smart actuators in our systems to deploy the wings, deploy the landing gear applications. To many such applications are there in the aircraft and missile fields. So the distribution of intelligence among all the components of the automation system transforms the centralized supervision systems into distributed intelligence systems. The interconnection of number of intelligent objects which produce or consume informations via communication systems associated with global management system. Local computing power generates locally available informations for the overall supervision system or for the smart instruments. Actuators diagram is shown here. The actuator database, you can see specific work available at the required frequency, number of actuators needed, reliability and toughness, power required. So for an actuator to be smart, its efficient collaboration with sensor is at most important. The sensor senses the stimulus from the environment under investigation. The actuator then acts as a muzzle and gives the required force for the actuator movement. So you can see there are various composites used in different aircrafts and missile applications. This is one diagram which is showing self-healing composites. So in composite is a layered material. We can embed some of the resins in the form of a liquid in the smart composites. Whenever the composite gets delaminated because of the hostile environment, the resin, whichever is kept inside the composite, will get break, and the resin will flow into the delamination area, and again it gets bonded. So that is the way we can repair the composites remotely. This is called the self-healing of the composites. So we can see achieving materials that are able to repair themselves after damage, the same as what biological samples do, was an important issue. Using such smart materials would decrease the need for continuous and expensive supervising, repairing, and difficult reinforcing. This matter is more important for cases such as space stations, underground submarines, and sensitive nuclear foundation constructions for their limited access of supervising the technicians. Suppose in space, if some structure gets damaged, it is very difficult to go and repair there. Suppose if you embed such self-sealing composites in the structure, so whenever the structure gives away, the self-sealing capability will make the structure all right. So, however, in the best conditions where supervision or diagnostics are performed accurately, it wouldn't be certainly lead to a practical repairing. So, engineers try to model self-healing materials inspiring biological systems. By taking advantage of nanotechnology, engineers imitate healing mechanisms of living organs to accomplish the strategies of self-healing materials. Inspiring function of blood cells in blood clotting motivate researchers to make microcapsules filled with healing agents. This self-healing is the practice came by seeing the normal human being, how when something happens, how the skin gets the stoppage of the blood will happen automatically. So in the same manner, we want to mimic the structures in engineering also with the self-healing capability. So self-healing systems, choosing the best system among the available mechanisms, choosing the most practical healing agent concerning main composite materials, containing sufficient healing agent supplies to perform efficient heal, representing suitable reaction against the threat using healing agent, low viscosity and high capillary for heating agent to sufficiently penetrate to micro cracks, preventing damage propagation by performing sufficient healing procedures, preventing catastrophic damages in basic recovering structures into their initial, restoring at least 50% of initial strength. So you can see this diagram clearly gives you the idea how the self-healing capability will be achieved in a structure. So you can see microcapsules, catalyst are available in the composite. When the crack happens, crack will get initiated, and the crack will damage that capsule, microcapsule, which is embedded in the structure. That microcapsule will have small resin packets, so that resin will flow into the cracked region and it gets filled, so that the structure will become again operational. So in this method, a tiny spherical microcapsules which are filled with the healing agent are embedded in the main composite, accompanying catalyst in main composite. Usually healing agent is made of dicyclopentadiene. that is easily polymerized in the presence of a catalyst, and it transforms into a hard substance. So I will briefly explain about composites in my next session. Just wait, I will share the screen. Are you able to see my screen, madam? Okay, advanced composites for aerospace applications. Till now, I have talked about smart materials, which is an emerging field, and we are in a small way, we have also adopted using smart materials. So advanced composites, which we are already using extensively, I will be explaining with some of the case studies. I will be just briefly telling about composites. What is composite? Composite materials can be defined as a combination of two or more materials differing in form or composition on macro scale, but acting in concert in combined form, retaining their identities across interface between one another. So as you see, fibers plus resin is equal to composite. So one constituent is called reinforcement, and the other one which is embedded is called the matrix or resin. So why composites are gaining so much of importance? These are the main reasons: high specific strength and high specific stiffness compared to metals. So tailored directional properties, ease of fabrication, redundant load paths we can create, good fatigue resistance, inherent damping capabilities, versatility, high corrosion resistant. So when compared to metal, with respect to weight, composites will give more strength compared to its strength to weight ratio. So high specific strength and high specific stiffness, these two properties makes composite structures ideal for aerospace applications. So composite materials basically consists of two main materials. One is called fiber and another is called resin. What the fiber does? Fibers carry the principal load carrying members and provide necessary strength and stiffness. So fibers are all drawn into small wire kind of material. So these have very low internal defects compared to the bulk materials like metals. And fibers will have very high L by D ratio. What is the resin? Resin supports the fibers and it protects the fibers, gives shape to the structure, acts as a media for load transfer between the fibers. A resin has a lower density, strength, and modulus than fibers. So fibers are useful only after they are bonded together to take the form of a structural element that can carry loads. Combination of fibers and matrix will result into lower density. So when you see the stress strain diagram, the fiber will have high tensile stress and low strain, and resin will have low stress and high strain. So when you combine both of these in proper proportions with fiber volume fraction, that is an important property. So depending upon the ratio of the fiber and resin, composite properties can be achieved. The properties of the composites are mainly determined by the properties of the fiber, properties of the resin, and the ratio of fiber to resin in the composite. That is called fiber volume fraction. This property is very, very important. Fiber volume fraction. The geometry and orientation of the fiber in the composite dictates how the composite should be made. Then there are various types of composites which is classified depending upon the matrix, depending upon the reinforcement. So there are basically metal matrix composites includes mixtures of ceramics and metals such as cemented carpets and other cements, as well as aluminum or magnesium reinforced by strong and high stiffness of the fibers. There are other composites called ceramic matrix composites. Least common composite matrix, aluminum oxide or silicon carbates are the materials that can be embedded with the fibers for improved properties, especially in high temperature applications. Polymer matrix composites, which we are widely using in our missile applications. These are thermosetting resins, mostly epoxies or phenolics, which is commonly used with the various types of fibers like e-glass, carbon, boron, silica. So there is another variety of composites called carbon-carbon composites. Here, the with the high temperature capability will be achieved by converting the resin also into carbon. The reinforcement is already carbon, and the resin which is used as a binder, that also can be converted into carbon by various cycles, and it also becomes carbon. So carbon-carbon composites are very useful in high temperature applications, which we have developed for nose cones of re-entry vehicle systems and carbon-carbon brake discs. So classification of composite materials. This is basically, we can define it as a fiber reinforced composites and particle reinforced composites. So particle reinforced composites will have, depending upon the orientation of the fiber, random and preferred orientation. Fiber reinforced composites are basically single layer composites and multi-layered composites. Multi-layered composites are used extensively in all the aircraft applications. These are called unidirectional reinforcement, bidirectional reinforcement, random fiber orientation, like this. Then classification of fibers. So fibers are the primarily load carrying members. Classification of fibers based on materials, composition, and precursors. We can see varieties of fiber in the market. Glass fibers are widely used for all commercial applications. E-glass, S-glass, D-glass, R-glass, high silica, and C-glass. So carbon fibers, which are extensively used in aerospace applications, these fibers are costly and available in limited quantities. So these are basically based, carbon fiber is also again based on the precursors available, like rayon-based carbon fiber, then pitch-based carbon fiber, and high-strength or modulus fibers. So depending upon the application, we choose the fiber for which application, which fiber is suitable. Based on that, we use the reinforcement. Then aramid fibers, which is basically used for impact applications, like bulletproof jackets and bulletproof materials for automobiles. Then boron fibers, which is used limitedly in different applications. So you can see the fibers basically like our threads. So this is also can be weaved into different shapes to get the different properties. So you can see the types of weaves we can relate it to, like our textiles: plain weave, twill weave, satin weave, and basket weave. So these are the properties which is evaluated for this carbon fabrics. You can see the various properties like good stability, good drapability, low porosity, smoothness, balance, symmetrical, low crimp. So these are the various types of weaves which is given here. So generally we use satin weave, which is having all the good qualities, so that the fiber will take the shape of the component whichever you want. So you can see here I have shown some of the photographs of the fibers, how it looks like. E-glass fiber, which is white in color, it is made of glass material. Then carbon fiber, which is black in color, and the yellow in color is called Kevlar fiber. So the fiber which is available in the form of a bundle, that is called roving. The rovings, when we weaved to the different styles by using satin or twill weave or plain weave, so that becomes the fabric. Generally, fabrics are available in a width of 1 meter or 1.2 meter and continuous lengths of about 100 to 200 meters. So various types of fibers are shown here for different applications. You can see rayon-based carbon fabric used for ablative components, fan-based carbon fiber, which is meant for aerospace structural composites. Kevlar fiber, as I explained, it is meant for ballistic applications and some of the structural applications. High silica fabric, which is meant mainly for thermal insulation of composites, which we are using extensively as an insulative material in between the nozzle for the throat backup and divergent liners. E-glass fiber is meant for commercial applications. Basically, wherever the low strength is required, these fibers are used. We are using E-glass fiber extensively for jet deflectors and different ground-based applications. D-glass fiber is used for dielectric applications, basically radomes. So you can see how these basic three varieties of reinforcements, aramid, carbon, and glass, in different properties, how it looks like. You can see high tensile strength, high tensile modulus, high compressive strength, high compressive modulus, and flexural strength, flexural modulus, impact strength, then interlaminar shear strength, in-plane shear strength, low density, high fatigue resistance, fire resistance, thermal insulation, electrical insulation, thermal expansion, and the cost. If you see, the carbon fiber will take the most of the properties better in terms of properties. So that's why carbon fiber is used extensively in aerospace applications. Compared to cost-wise, carbon fibers are costlier than glass fibers. But properties, other properties which are very useful, so you will get the better component with less weight. That's why composite carbon fibers is gaining a lot of importance. For ballistic applications, aramid fiber is used where we can get the impact resistance, like bulletproof jackets, bulletproof vehicles can be used by using a aramid fiber. So there are basically two types of resins. The primary function of the resin in composite materials are to transfer stress between the reinforcing fibers and to protect the fibers from mechanical and environmental damage. The resins are divided into two major groups, thermosetting resins and thermoplastic resins. If you can see the thermosetting resin systems, basically, there are epoxies, phenolics, vinyl esters, dismalmate resins, unsaturated polyester, PMR15, cyanide resins. Thermoplastic resins, they are basically polyethylene, polyvinyl chloride, polypropylene, polycarbonate, nylons, PETs, polyether ketones, polyphenyl sulfides, polyether sulfones. So we are basically using thermosetting resins in most of our applications, except one or two applications where thermoplastic resins are tried out in making the radome applications by using a peak material, polyether ether ketone. So thermosetting resin systems, epoxy resin system and phenolic resin systems, basically these two materials are widely used in our aerospace industry. If you see the epoxy resin systems, there are two component resin system, resin and hardener, and it has adhesive in nature. Resin has adhesive in nature, no byproducts released during the curing, and it gives high mechanical properties and used for structural applications. If you see phenolic resins, which we are using widely for our missile applications to make the structures in nozzles, which has to withstand very high temperature, and the re-entry vehicle structures, we are using phenolic resin. There are two types of phenolic resins. Rhizole type, it is a self-cross-linking phenolic resin. Then Novaloc requires a hardener. So this phenolic resin will be high char yield material and ablative material. So volatiles are released during the polymerization process as a byproduct. This has to be taken out by using a vacuum application. The equipment which we used for polymerization is called autoclave, which have the simultaneous heating and pressurization application, and simultaneously we can vent out the byproducts by using a vacuum. Voids forms during curing in phenolic resin that we have to avoid by using the vacuum bagging technique. Phenolics are comparatively having poor mechanical properties. When you compare the same reinforcement with epoxy and phenolics will lead to low mechanical properties. Epoxy materials will have high mechanical properties. So I will briefly explain what are the different manufacturing techniques in the composite, and I will go for case studies also. So this is one of the important process in composites called filament winding technique. So the machine similar to a lathe machine. In lathe machine, we remove the material from the bar stud. Here we deposit the material on a mandrel which is between the centers. So the filament winding process produces hollow shaped products. It is a wet winding process, fiber and resin, or we can use the tauprex for when tauprex it is called dry winding. So continuous fiber reinforcements are precisely positioned in a determined pattern on a rotating mantle. As you see in the diagram, the fibers are put at an angle. This is called helical winding. If you put parallel to the axis, it is called hoop winding. This is a computer numerically controlled machine which have 4 axes or 5 axes. We can place the fiber in whichever the angle we desire or the designer prefers. We can place across the parallel to the fiber or at an angle to the axis of the component or parallel to the axis of the component also we can place the fiber, so that we will get an optimum structure to carry the desired loads. After number of layers, curing is carried out in a oven, and finally the component can be extracted. By removing the mandrel, the cylindrical component can be extracted. Here you can see the machine which we are having in our advanced system laboratory. This is a filament winding machine which is we can make 3 meter dia components around 16 meter length. It looks like lathe, but in lathe we remove material, but here we will deposit the material by using the carriage. So filament winding is possible for both axis symmetric components and non-axis symmetric components. So there is another technique called tape winding technique. It is similar to filament winding machine, but in filament winding machine, filaments will be wound on a mandrel. Here, the tape is a part of the fabric which is already weaved into a different shape. The tape can be put onto the mandrel with the help of preheating arrangement, and also the tape which is wound on the mandrel, we can apply some force and we can make a nice components. Very thick components can be realized in this tape winding process, which is used for nozzle applications. As you see in the diagram, divergent cone shaped articles and cylindrical shaped throat backups are manufactured by this method. So this method is extensively used in our aerospace applications like nozzle applications and some other components, which is used for different nozzle materials. There is another important technique called compression molding. Compression molding is a process where we use hydraulic press to make the components by using a punch and die. The charge is placed in between the punch and die, and simultaneously the mold is heated and the pressure is applied to consolidate the polymer matrix composites. So here materials like fiber fabric impregnated with resin charged to a specific size mold closed and heated under pressure. So you can see we have realized nice components by using this technique, which is around 1 meter dia and around 400 mm thick also. This is like a forging kind of material we can make, and then we can again machine it the required shapes required for the nozzle components. Here the charge is placed in the cavity of a matched die mold in an open position. Mold is closed by bringing two halves together by using a hydraulic arrangement. Pressure is exerted to squeeze the resin so that it fills the mold cavity. While under pressure, the mold is heated and the polymer is polymerized to get the nice composite components suitable for highly thick components. So here you can see this is one of the product which we have made. Here the mold is filled with carbon phenolic prepeg flakes and it is put into the cavity of the mold. And the punch is also from the top, it comes and gets closed. Once it is heated and simultaneously the pressure is applied to make the convergence of a flex nozzle system. Here we can get high density composites, but variation in strength and thermal conductivity because of the flakes configuration, high volatile content, and giving rise to good compressibility. There is another important process called vacuum bagging method and autoclave bagging and pressure bagging. These are all called match die molding methods. Here one side we can use the mold, and the other side a flexible bag kind of material that is called vacuum bag, where we can make the components, and it will be cured in autoclave. So by here, where we can apply simultaneously the pressure and heat also, so that we will get the nice polymerized composites. In some applications, we can apply the pressure through a bag by using thermofluids. So we can apply the heat. That is also called the pressure bag technique. The composite material is pressed between heated matched dies. Pressure required depends on the flow characteristics of the feed materials. The feed material flows into the contours of the mold and cures at high temperature. In this process, near net shaped components can be obtained. Here we can see the conical part, which is made at one go. Suppose if you in metal, if you want to make this type of cones, you have to make the sheet and then cut into the shape and then roll bend and then weld. But unlike in metals, composites, if we have the mold, we can place the fibers and put the both male and female molds, and you heat the final component you will be getting. So there is no machining. Near net shape components you are able to get. You can see the another plate which is having ribs on both sides, which is also made in one go without any machining. Only edge trimming is done to realize the final component. So there is another important technique which is widely used in nowadays, even in aerospace industry also, vacuum assisted resin transfer molding. In this, mold is made one side, and the other side it is a flexible membrane which is used, and the reinforcement is put onto the mold, and the resin is injected from one side to the other side, so that the resin flows all through the reinforcement, and if you finally get the composite. So this machine, techniques is widely used for making large size components like wind turbine blades, and this method is gaining a lot of importance because of the we can get without any defect the components, and large sized components also can be realized at a very small reasonable time. So VARTM is a single molded molding process. The dry preform reinforcement or core materials is placed into the mold. A vacuum bag is placed over the top to form the vacuum tight seal. A distribution medium is used and laid up on top to maintain the even distribution of resin to facilitate the flow of the resin through the reinforcement. So here the resin has to flow through the entire layers of the reinforcement layers and to the entire area. So for this, a lot of simulation techniques are also used. A lot of softwares have been developed in order to see that the resin flows through the entire surface of the component, so that there is no resin rich layers or resin lean areas. So this method is widely used for commercial applications. So this is a normal method, wet layup or hand layup process. Here one side mold is used, then the fiber is placed, and the resin is taken and it is spread across the reinforcement by using a hand or spray layer process. This is basically used for commercial applications. The most important process in terms of current aerospace production is the hand layup of prepregs. In spite of steady progress on to replace the hand layer process with automated process, it still persists as the method by which at least half of all the advanced aerospace composite structures are made. It is extremely flexible and capable of making wide variety of shapes. So preparation of the mold, application of the release agent, application of gel coat, hand layup, curing, trimming, and finishing. So hand layup process is widely used in aerospace application also. We can make varieties of components by using prepegs, wide variety of components. We can put the fibers wherever the extra thickness is also required. Variable thickness components also we can realize by this process. Just like hand layer process, there is another technique called spray layer process, which is used for commercial applications and mass production. Here the fiber and resin both are cut and it will be sprayed by using a gun. This layer process is also uses one side mold. So variation of a hand layup technique. Mold is treated with release agent. Gel coat layers are placed on the mold. The gun sprays the mixture of chopped fiber and resin and a catalyst onto the mold. Rolled out to remove entrapped air and give a smooth surface. Poor rollout can induce structural weakness by leaving air bubbles, dislocation of fibers, and poor wet out. Here, whatever the resin entrapped between the fiber and resin has to be squeezed out by using various techniques, by using a hand roller or by applying a vacuum bag technique. This is another important element which we have done by using a filament winding technique. Here you can see grid stiffened plate which is made by using a POP mandrel with groove cutting. So we can place the fibers on the grooves and then subsequently on the outer periphery so that we can make grid stiffened shells. With these shells, we can reduce the weight of the component and we can achieve the desired properties. So these are the new concept which we are extensively practicing for the manufacturing of airframes. Here we can also make the components with varied angles also at an inclination. So like a lattice structure we can call. So with that also we can make. Here we can see POP casting and groove cutting is the important function. Then hoop and axial stiffeners in the winding using UD or prefect tape. Then skin winding by using different angles. Then vacuum bagging and autoclave curing. These type of structures we have realized and load tested successfully for the different airframe applications. So as high as 2 meter dia components and length around 800 meters have been already realized by using a filament winding technique. One minute, I have some more slides. Hello, are you able to hear me?
Yes, sir, we are able to hear you.
This is another important technique, layup technique called rosette layup technique. In this,
yes, sir, we are able to see that.
In this, we are able to make the component with different hand layup techniques only. But here you can see the outer layer of the fiber is inside. It is like a cylindrical component or conical component we can make by using this technique. The layer of the fiber is positioned in such a way that one edge of the fiber is in the inside diameter of the component and the other edge is on the outside edge of the cone. So this fiber, in this way we are making convergent liners of a nozzle system where edges are only exposed to the flame. By this way we can reduce the erosion and increase the flow rate and increase the resistivity of the component. This is another important technique called vacuum bagging technique, which I already explained, where we can apply pressure through 1 bar atmosphere. 1 atmospheric pressure can be applied through a vacuum bagging technique, where there is no autoclave. Such components we can use by vacuum bagging technique we can realize. So here this is an equipment called autoclave curing. Autoclave is a pressure vessel where we can apply simultaneously pressure, temperature and vacuum to polymerize the composites. This method is widely used in aerospace industry to cure the components. We get good consolidation of the parts through this method. So here you can see this is a pressure vessel where we can keep the component inside and simultaneously we can apply heat and pressure through air and vacuum also in order to extract the volatiles from the component. This is an important equipment in the aerospace industry. So here you can see the actual equipment which is installed in our laboratory. It is around 1.5 dia and 3 meter long, with a door mechanism like a pressure cooker concept. The door is designed. Then we can heat the component up to 400 degrees centigrade, and we can apply pressure around 20 bar, and vacuum lines are given for extracting the volatiles from the component during pressurization. 6 vacuum lines are available, and we can apply maximum 1 bar negative pressure in the component. So this is another important technique called impregnation of the fiber with the resin system, called impregnation plant or pre-peg plant. Here you can see the schematic diagram. Here the fiber which comes from the unwinder and gets heated into preheating chamber where volatiles are evaporated. You can heat up to 80 degree or 100 degrees centigrade, and then it gets into a squeezing station where the resin is available, and it gets mixed with the resin, and the excess resin is squeezed out between the two rollers called squeezing station, and then it gets heated onto heating zones 1, 2, 3, 4, where each zone is maintained at different temperatures so that all the volatiles are getting evaporated, and it gets cooled in a cooling roller chamber, and then it gets unwinded onto a roller. So in this way we can make prepegs and keep under cold storage for the minimum of maximum of 1 year. So here we have to maintain these properties like volatile content. We have to maintain Chang's index, wet resin content, and tackiness of the prepeg. So here you can see this actual prepeg plant which is available in our advanced system laboratory, where we regularly impregnate the fabric with the resin system by using phenolic resin. So this is a vertical impregnation plant we call. Here we are making different varieties of fabrics like carbon fabric, rayon-based carbon fabric, pan-based, high silica fabric, e-glass fabric. So normally the fabric comes in the width of 1.2 meters. In this impregnation process, we have to control the resin content, volatile content, and tackiness content. So for this, we have the different parameters like squeezing, then heating, then cooling. All these parameters we have to control while doing the impregnation process. So here we can see design and development of composite technologies where we can use these technologies. So primary structures we can realize by using these technologies: airframes, composite rocket motor casings, and canisters. We can use very high temperature resistive applications like re-entry vehicle structure, which can withstand up to 3000 degrees centigrade. Then ultra high temperature composites, carbon-carbon nose tips, control surfaces we can get by using this composite materials. Then structural applications, we are using radomes where the front part of the aircraft nose cone is made of radome, which is made in polymer to enhance the electromagnetic radiation capabilities. The inside antenna will be there. Antenna will be emitting the electromagnetic waves and receiving the electromagnetic waves in order to detect the enemy where enemy aircraft or targets are placed. Then secondary structures, we have different types of secondary structures like warhead casings, ablative liners for nodules, thermal protection system components can be realized. So there are various types of machineries used and materials used in composite technologies. We have a 5-axis filament winding machines, which is meant for using different types of axis symmetric components. Then autoclave, then we have a CNC tape-on composite machine, lattice structures. Then all the composites which are made, we have to undergo an ultrasonic testing, that is called non-destructive examinations or radiography. Then we are making electro-transparent radomes for different applications. And we have a different compression molding techniques. For that, we are using different capacity of presses called 300 ton, 500 ton capacities. And we are using the resin transfer molding techniques also. The basic fiber is used in our setup is glass fiber, carbon fiber, Kevlar fiber, and quartz fiber. Then resin systems which we are using regularly: epoxies, phenolics, cyanide esters, polyetoconamides, and low-loss polyester materials. Here I will be explaining some of the case studies which we have developed in our advanced system laboratory for different aircraft application and missile applications. Here we can see this is an indigenously made combat aircraft by our aeronautical development agency. This aircraft is called Tejas, which is completed all its developmental tests and it is going in production. HAL is making around 100 aircrafts for the Indian Air Force requirements. So here you can see there are fuel tanks which is blue in color, which is mounted under the fuselage. Then in the wing, there are 3 stations: inboard, midboard, outboard. In the inboard and the midboard, we can keep these fuel tanks. So these fuel tanks are developed in composites, which I will be explaining in further subsequent slides. So these tanks are externally mounted jettisonable fuel tanks for carrying aviation turbine fuel for the combat aircraft. The composite drop tanks are developed first of its kind in India with state-of-the-art technologies. It is lightest in its class, designed for lightning protection and has least radar cross-section. Drop tanks are mounted externally either in inboard or midboard of the wing stations or under the fuselage. In order to enhance the flight duration, the drop tanks are carried in the aircraft. When the aircraft requires more fuel for its extended flights, it transfers the fuel from the externally mounted fuel tanks to the main fuel tank, and the empty tank can be jettisoned in order to increase the maneuverability of the aircraft. Here you can see the tank inside will have a lot of baffles, bulkheads, and structural components, then sensors, then for filling various cutouts, for filling the fuel and transfer the fuel from the main craft to the drop tank and drop tank to the mother tank. Here we have developed 3 varieties of tanks. One is called 800 liters tank, which is having diameter of 550, length around 4.5 meters, weighing around 78 kgs. When it is compared with aluminum tanks, these tanks are almost half of the weight. So that's the reason these tanks are developed in composites. Then 1200 liters inboard tank, you can see the diameter is 640, length is around 5.04 meters and weighing around 100 kgs. It can carry 1200 liters of the fuel. So this aircraft is having varieties of cutouts in order to fill the fuel, and in order to have the safety of the fuel, we have relief valve and other things. And in order to have the connection between the mother tank to the main tank, we have fuel valve and air valve connection. And in order to carry this tank on the wing, we have ejector release unit and ERU, so which is embedded in the tank. So these are made by hot melt epoxy pre-pack technique, which is the main process technique which we are used, called hand layup and autoclave molding and a female mold. So here we can see the tank consists of varieties of components like sheet metal components, bulkheads and brackets, metallic parts, sheet metal parts, piping, electrical, rubber, metal fasteners, and line replaceable units. Varieties of raw materials also gone into this, like epoxy prepakes, alumesh prepakes in order to protect the tank from the lightning, then adhesive films, epoxy resins for the impermeability of the fuel tank, then electrodag for giving continuity for the electrical application. Sealants, varieties of sealants are used in order to protect the tank from the leakages, and structural adhesives are also used. Here we have developed through 2 main important processes called co-curing and co-bonding. Here we can see a lot of aluminum components are embedded into the composite. Here only adhesive is used in order to get the bonding between the aluminum and the composite. There is no riveting in it. So process design of all the composite components, and we have designed and realized the different types of molding tools, assembly fixtures, pressure and leak test fixtures, structural rig, and for the center section assembly, functional test rig, qualification test rig. These are all the things developed, which I will be explaining in subsequent slides. So here we can see the different production techniques what we have followed for the development of the drop tank: compression molding technology, autoclave technology. These are the varieties of components which we have realized. So co-curing and co-bonding technology developed for aluminum cap with E-class prepeg and nose cone forward and rear cone aft, then aluminum joint ring with E-class prepeg for the nose cone aft and rear cone forward. Then designed and realized templates for surface development cuttings, transfer foil technique adopted for placing plies at the desired place and orientation. Process and cure cycle developed for autoclave molding, compression molding, oven curing, and thermoforming of foam. Here you can see the shells are made in a variety of thicknesses. So the tank is not of uniform thickness. It is having thickness, varying thickness at varying places. And we have different thicknesses wherever there is a cutout requirement. We have placed extra fibers there in order to give the reinforcement for the cutout reasons. So here we have developed varieties of shapes of components like hat section, brackets, then tire kind of sections. These different kinds of sections are developed. Here we can see the different cure cycles also developed for different applications like autoclaving, compression molding technique, which is shown on the right hand side. So here we can see the varieties of toolings have been developed in order to realize these components. These tools are made of cast iron metal and used for realization of the components. One tool can be used for making maybe 500 to 1000 components. So these tools are made for different applications like skin shells and bulkheads and a lot of stiffener materials. So open die molds for skin shells, which is the tool can be split into two parts. Once the component is made, the tool is made into two parts and the component is ejected from the mold. Like match die mold tooling for brackets, we have developed compression molding tooling for the bulkheads. So the main features of tooling are longitudinal joint for easy extraction of the components, then grooves for rubber gaskets to prevent leakage of the joints, metal inserts in the tool to have flat depressions on the component to mount LRUs, then automatic rotation of the tool for the easy handling during layup of the skin shells, then built-in vacuum ports, provision for locating of the end rings, in situ molding of the rings. So in the tool, we have put a lot of mechanisms and impressions to get the final shape of the component. We don't have any machining in this composites. We will get final near net shaped component. Here we can see a lot of sub-assemblies which are going on to the middle section of the shell, center shell we call. So there is a rack assembly which is made of small aluminum parts. Then we have developed a lot of drill jigs also in composites. So these are the lot of sub-assemblies like bottom frame assembly, rack assembly, ceiling bulkhead assembly, then fuel pipe assembly, hosing assembly. There are a lot of sub-assemblies which is going into the fuel tank. So here these are all the sheet metal parts which are going inside the fuel tank. So we can see support bracket, air pipe, support bracket, transfer pipe, clamp assembly, bottom frame assembly. Then there are various anchor nut riveting assemblies for the fuel tank. Then cross beam, lug well frame, I beams, joint entrings. These are all the metal components which are going inside the fuel tank. So composites are basically porous in nature because of the fabric weaving nature and the method of manufacturing. Composites will be slightly porous. So, but the fuel tank should be non-porous. For that, what we do resin coating inside the fuel tank in order to make the tank leak proofness. So here we have developed a mechanism for the resin coating. So we heat the composite from the externally mounted IR lamps, and resin coating is given inside the tank, and it gets rotated so that the uniform coating is applied all throughout the surface. For that, we have developed different varieties of fixtures. Then once the tank is coated with resin, again we do test for leak proofness, and we do a lot of assemblies. The cone is made in two parts. These are all get assembled as shown in the diagrams. And then finally the tank is assembled and tested for its leak proofness by using different types of fixtures. So here we have to incorporate a lot of sensors inside the tank. As I explained earlier, There is a high-level sensor, low-level sensor, fuel transfer valve, junction box assembly in the fuel tank. So the fuel tank, when it is assembled to the bottom of the aircraft, the pilot should be able to know how much fuel he is having in this tank. All this information is fed to the pilot dashboard by using this electrical cable harness and the sensors which is embedded in the fuel tank, and it gets the pilot will be able to know whether the tank is connected to the aircraft or not, how much fuel is available, and what is the information when he can jettison. All those things can be available to the pilot on his dashboard. So once the tank is made, we do a lot of tests for its acceptance test and qualification test. Here you can see the tank is tested for the structural test application by using hydraulic actuators and the power pack, where we will apply 2 tons load, 4 tons load onto the lugs for 5 minutes and see the structure will be able to withstand that load. Similarly, we will use the fuel leak test also we carry out, and a lot of pneumatic tests also we carried out for qualifying the different joints like junction box, housing, ceiling, bulkhead. So we do a lot of acceptance tests before going to the final assembly. So here we have developed one functional test rig for conducting various tests on the drop tank. Here you can see this is a completely automated, computer controlled automated testing where we can perform a lot of operations by using this rig. Here you can see the drop tank when it is mounted onto the aircraft. In the similar way, we can mount on this rig and find out what is the empty weight tank, what is the full fuel weight, unusable fuel, undrainable fuel. By having the load cell at 2 locations, we can carry all this information we can get by filling the tank with the fuel and draining the tank with the compressed air, and we can find out all these things. So simultaneously in the same rig we can do all these functional tests like leak check by air, leak check by fuel, strength test or pressure test with the fuel, around 20 psi for 5 minutes. Then refueling check we can carry out at 4.5 psi or more than 150 liters per minute. The transfer rate we have to check, refueling transfer rate. Then transfer check also we will do at 100 lpm from the drop tank to the main tank. So like this we can conduct a lot of tests by using this rig. So in the similar way, we have to do qualification test of the tank. Whatever the loads coming onto this tank, which is aerodynamic loads, are converted into uniformly distributed load and then point loads, where we can apply the loads by using this tree. We have applied the loads on 3 axes like X, Y, Z simultaneously and measured the reactions loads by using different types of load cells, and the strain gauges we have bonded, and we have measured the strains at various locations, and we have measured the deflections by using a linearly variable differential transformers. So this simultaneously we have pressurized the tank by filling the tank with water up to 15 psi. So this is the one-time test which we have successfully carried out, and all the measurements are within our predictions. So this is qualified for the flight. So here we have shown the different strain gauge results, which is in micro strains predicted versus measured. Measured results are less than the predicted results. In the similar way, in the bottom we have shown the deflections, which is less than the predictions, and the structure is qualified for the further use. Here there is another case study which is meant a closure plate, RVS composite closure plate, which is meant for re-entry vehicle structure. This is developed by composite press molding. So this is made of carbon fiber and phenolic resin, which the plate has to withstand severe thermal load. That's why we have made with the phenolic resin, and ribs are also incorporated in order to avoid the deflection of the components. This component is made in one go by using a two-sided mold in a compression molding technique, and for the sake of passenger cables and other things to move, we have made small cutouts. So this is a lightweight plate which is made of using one side ribs and one side plain surface. Both sides of the plate should be very smooth. Then it has to withstand a severe thermal environment for re-entry conditions. Provisions are made for passing the cables and other VTP thruster nodules. So it should be fastened at the aft end of the bulkhead of the re-entry vehicle structure. The inside packages of the RVS system should be protected from hyperthermal environment. We have selected an easy manufacturing route that is called compression molding route. So here we can see pan-based carbon fabric and phenolic resin is chosen as the fabric and resin materials. The process is impregnation, and we have made surface developments, hand layer, match day molding, hydraulic press curing, non-destructive testing, and machining. So this is the fabric specifications which we have used. Then this is the phenolic resin, which is made of IVR or Apron. So there are two manufacturers for making of this resin system, phenolic resin. These are the properties: viscosity, specific gravity, and point of trouble, volatile content, solid resin content, then free formaldehyde, free phenol. This is the properties which we are measuring before the impregnation, like specific gravity, viscosity, point of trouble, volatile content, and solid resin content. This is the drawing of the component. This is the model. This is the cutouts which is indicated after making the component. This is the final model with cutouts. This is the one side of the tool. This is another side which is having a provision for heating. This is the press used for making this component. This is the final different types of developments which we have used for making the component. This is the sequence of layers which we have put for realization of this component. This is the cure cycle followed. This is a compression cure cycle which we have applied around 200 tons for realization of this component. Depending upon the surface area, we can calculate the load applied onto the component, and this is the cure cycle which we are heating up to 160 degrees centigrade for the duration of almost 500 seconds, 500 minutes. This is the final shape of the component which we have used. This type of plates we have almost made around 40 numbers for various applications. These are the tests we have conducted, like ultrasonic test. Then we are doing sample tests also to find out the resin content and density. Then dimensional inspection test. This is the machining we have carried out in order to give the final shape and the requirement of the passengers to go on to the component. This is another component which is made by using a carbon fabric and epoxy resin system, which has to withstand very high load requirements. This component is having ribs on both sides, because in order to avoid deflections, we have designed a plate in such a way that it will have ribs on both sides, and it is made in hydraulic press. So these are the materials used: carbon fabric, epoxy resin. Then process is hand layer process and match day molding, hydraulic press curing. This is properties of the components which we have evaluated by making the laminates. Here you can see longitudinal modulus, transverse modulus almost the same, shear modulus, Poisson's ratio, then longitudinal strength, compressive strength, transverse tensile strength, transverse compressive strength, shear plane, in-plane shear strength. Then these are the developments which we have used for making realization of this component. These are the layer sequence, different layers at rib thickness also we have shown here. This is the plate which we have both sides extra stiffeners on the plate both sides. So this is the cure cycle which we have used. This is the plate photograph which we have developed, which is having 8 ribs on both sides, the same similar shape. So here you can see the thickness cross section of the component. Here you can see the plate is tested ultrasonically and found good condition. Then we have developed samples also from the component and conducted density and resin content test, dimensional inspection also carried out by using CMM. This is the final component which is having small cutouts in order to passengers, in order to give the provision for cables and pipes. This is the component drawing. This is the final different cutouts shown in the component. These are the properties which we have made by using the travel coupons, ILSS, flexural strength, flexural modulus, tensile strength, tensile modulus. These are the maximum number of specimens we have tested. Minimum value observed, maximum value observed, and the average value is given here. Then this is the load test which we have conducted in order to qualify this plate. So we have applied different passengers like air bottle propellant tanks are situated in this component. That load experienced during re-entry conditions are simulated by using actuators like 5-ton actuator at 2 locations and 10-ton actuators at 1-ton location. This is the schematic diagram. Then this is the actual test done at our structural material test facility by simulating the loading conditions. Load is applied and we have measured strains and deflections at different locations in order to qualify this plate. So this is the finite element methods expected deflections. These are the measured locations. We have placed 14 rosette type strain gauges in order to qualify this plate. These are the radial strains. These are the circumferential strains which we have estimated through FEM, and the results are compared to the actual test results, and then the plate is qualified for the observation. This is another important component is made in composite, jet deflector we call. This is used under the missile. When the missile takes off, the flume hits this deflector. The flume will have very high velocity and high temperature. That flume has to be dissipated in 2 directions without damaging the launch complex and the launcher related instrumentation. So the main function of the jet deflector is to split and deflect solid rocket motor exhaust gases to protect the launch vehicle from the environment, to minimize the exhaust impingement effects. So here you can see this configuration is the entire surface area is divided into different shapes of the lines, like sidewall liners, profile liners, and top of the component called ridge component. So here we have used basically e-glass fabric and the phenolic resin. This is the 2 materials which we have used, and we have made the impregnation. The e-glass fabric is impregnated with the phenolic resin in the impregnation plant, and the impregnated phenolic prepeg has to have this volatile content, chunks and dies, and resin content. Then the composite will be made separately, and it should have the properties like density, tensile strength, modulus, and ILSS. These are all the properties we have tested. Then this is a joining scheme of the different liners, which we have configured in order to protect the metallic deflector by using these composite liners. So these are the different types of liners which we have made by using glass, fiber, and phenolic resin. We can see the length of the component is around 4 meters, and almost around 1 meter to 2 meter width of the composite liners are made. So slant liner, ridge liner, horizontal liner, trough liner. So these are all used in the deflector. There is another important element which we have developed in composite is called flex nozzle system, which is used in the exhaust of the rocket motor, which can convert the pressure energy into kinetic energy and gives the thrust to the missile system. Here you can see the typical important properties of the nozzle is area ratio, throat diameter, exit diameter, length, weight, vectoring capability, duration, and maximum effective operating pressure of the rocket motor. Based on this, we have designed the nozzle. The flexing capability is obtained by using a flex bearing, which is made of alternate layers of steel and rubber shims, and the remaining convergent liners are made with composite carbon phenolic prepex, and divergent liner is also made by using carbon phenolic prepex. Here you can see various sub-assemblies called entry section sub-assembly, convergent sub-assembly, divergent sub-assembly, and flex nodule sub-assembly. Here you can see the schematic diagram of the nozzle system. Here you can see the various types of liners which are made schematically shown in this diagram. Here the nozzle is moved by using an electrohydraulic servo actuator, which gives the thrust vector control for the entire missile system. It can be moved in pitch and yaw directions with plus or minus 4 degrees. The various types of liners and the manufacturing process is shown in the figure, like thermal boot, then flux seal, then throat insert, nose insert, radiation shield, throat closure, then intermediate dome, then divergent liners. So different types of processes used are also shown in the figure. So this is a very convergent subassembly. You can see the various steps are explained pictorially. Throat graphite, then throat backup unit, then intersection subassembly, radiation shield, nose insert, then it gets bonded, then flux seal assembly, intermediate dome assembly, convergent subassembly. We have evolved the integration sequence, carried out all the interface details, realized the section, and it is tested for its leak proofness by using a throat closure leak test. So this is a divergent flow chart. We can see forend liner, aftend liner, then both bonded together, externally machined, internally machined, then it gets bonded to the structural backup. And we are making composite structural backup by using the different layers. Here it is shown that 18 layers, how we are using different types of concepts. So this is another important element called development of ablative liners by compression molding technique and divergence by tape winding technique is shown here. Here we can see we have made similar types of components by using compression molding technique, and divergent liners are made by tape winding technique. So these are the hardware which we have gone into the flex nozzle system, like convergent hardware, divergent hardware. So the composite liners are bonded inside these liners, metallic liners, in order to protect these structural elements from the hyperthermal environment. This is a flux seal molding and testing rig, where the alternate layers of metal and rubber is molded together in a compression molding tool, and the seal is made and the seal is tested for various types of bench test. We call proof pressure test up to 73.5 bar, null position test up to 53.8 bar, vectoring test up to plus or minus 4 degrees. So this is a nozzle container which we use it for the transportation of nozzle from one place to other place, which is having various features. And this is the setup where we are qualifying the entire nozzle system before integrating to the missile system. We do a lot of ground tests. For this, we have developed two varieties of rigs called trial actuation rig and integrated test rig. Here we can perform the following tests. The integrated test is carried out at root pressure, vectoring up to plus or minus 4 degrees in pitch and yaw direction, and simultaneously we can also actuate both actuators. During this test, we are measuring a lot of strains on different members called throat housing, forend and aftend ring. Then seal compression also we are measuring by using LVDTs. The actuator force is measured by using load cells. The deflections are measured by using inclinometers. Then bond integrity test also carried out by after the integrated test. So there is another important element in the missile system is called composite rocket motor casing, which is done by filament winding technique as explained in the previous slides. Here we can see this is the composite rocket motor casing, which is houses around 10 tons of propellant, which is having a 2 meter dia and around 3 meter in length. The one such similar case is which is having 4 meter in length, 1 meter dia, is done for structural test applications. So here we have developed this technology for different missile applications. So different types of composite rocket motor casings are made from 500 mm dia, 3 meter length to around 2.4 meter dia, 10 meter length casings, which can carry around 50 ton propellants, are also realized with this same technology. So here is the flow chart which is meant for realization of the composite rocket motor casings. Here we can see the mandrel is made by using foam and central shaft. Then the filament winding technique, the composite casing is made, and subsequently the skirts are bonded in order to make the complete casing. So these are the complete rocket motor stage we call it. This is having a propellant inside and igniter at the one side and the nozzle at the other end. So here everywhere composite is used extensively in order to gain the weight and in order to get the more thrust for the given propellant. So this is the pressure vessel made for realization of CRMC. Before realization of CRMC, we completely characterize the materials which we are using by doing a subscale motor. We have done all the characterization. Then these composite rocket motor casings will withstand to very high temperature environment because of its velocity and accelerations. So this outer surface has to be protected with external thermal protection system, which is made by silicone resin in order to protect the surface of the composite from the hyperthermal environments. So this is another variety of composite canister technology we have made. You can see the length of the composite is around 8 meter length, single shell wound in a single setup. So these are meant for storing the missile system and launching the missile system. This technology is also established on our. This is one of the tests where we have done the burst test in order to find out the design capabilities of the canister. So these are the another important components called radomes, which are meant for giving electromagnetic transparency. There is an antenna inside this radome, which gives electromagnetic waves to pass through this material and absorb in order to find out the enemy location. These techniques are used. These are the inevitable materials for the aircrafts for getting the desired functionality of the electromagnetic transparency. So we have developed varieties of radomes with varieties of materials like Kevlar, low-loss polyester, glass, polyetopolamide, D-glass, cyanide ester, E-glass phenolic, like different composites are made. So this is, I already explained, this is the structural steel which is made of different hoop and longitudinal layers. Thank you, madam. Hello?
Hello, sir. I'm there.
Madam, my lecture is over, madam.
Okay. So thank you very much, sir.
Thank you, madam.
It's a really very long time. So any questions from the participants, please? Questions from the participants are welcome. So Dr. Seshaya is telling it's excellent presentation. We welcome the questions. You can type in the chat window or you can unmute yourself. Hello. Okay. So shall I assume there are no questions?
Okay, madam.
Okay. So thank you very much for your time, sir. It had been an excellent session and an overall view of composites and smart materials as well. So I would like to say that we are also airing this on YouTube live.
Yeah.
Okay. So the link is also shared to the participants.
Okay, madam. Thank you. Thank you, madam.
On behalf of Aero Department and our HOD, Dr. Gupta, sir, who is currently busy with his personal work, he could not be able to join you. He will surely join you very soon, sir. Thank you very much.
Okay, madam. Thank you. Thank you very much.
Thank you, sir.
Thank you.